Today we are moving on to Chapter 8, and 8.1 deals with geometric dilations. So there are a number of transformations in geometry. Translation is something we've dealt with a little bit. Translations where you just slide stuff left and right, up and down. It doesn't change the orientation, doesn't change the size. All it does is changes the position. Uh-oh, he's on his phone. Oh, yeah. Maybe you should listen to this. What a good idea. Um, we can flip things using reflections. We've done a little bit of that. We can rotate things. That's not something we've dealt with. If you want to change something's size, then you dilate it. So changing a shape's size is done through a dilation. So a dilation is based on the position of some point. So here on the screen, I have a rectangle and I have a point. And then the dilation will come with a ratio. So let's say my ratio is 2. So whatever distance this is from my point of dilation, I'm going to double that distance. I'm going to take that distance right here, and I'm going to double it to right there. And I do the same thing with this one. So that's going to go to here. And what do you notice about my rectangle? How much bigger? It's twice as big. So let's say that this was 2 feet, and now the distance from my point of dilation to the top left side of the rectangle is now twice as far. Okay. What if I did a dilation of 3? Then it's going to land over here, and it's going to be 3 times larger. Okay. What if my dilation was 0.25? So we take this distance, let's say that distance is 4 feet. We divide it by 4, times it by 25%, and it would be right here, and I would get this little rectangle. And that rectangle is exactly 1/4 as big as the original rectangle. Okay. Well, what if I move my dilation point? What if my ratio, let's say my ratio is 2. What if I drag my dilation point to here? Will my shape still be twice as big? Yeah, it's just going to be closer. So I take that distance and I double it, and I get a rectangle that is twice as big, but it's just closer than it was before. What if I put the dilation point inside the rectangle? So what if I move this to right there? What's going to happen? My rectangle will be twice as big, and it will just cover that. Okay, so I have a little geometric program that I'm going to show you. All right, so let's build a polygon. Okay, and then I put a dilation point, and I'm going to tell the computer this is my dilation point. And then transform, dilate, and then I have to pick a ratio. So let's say my ratio is 3/1. So this is my point of dilation. This is my original figure. And every point on this polygon gets dilated to be 3 times as far away. And if I move this point, notice the position changes, but the size does not change. And if I go inside, that's how dilations work. Okay, so let's do transform Dilate, let's do 2/3. So now the new figure is 2/3 as large as the original figure, and that point of dilation is going to move it around. Does that make sense? So the ratio will determine how big the shape is compared to the original shape, and then the point of dilation will determine where that new shape lands. So if you just want to make a shape bigger or smaller and keep it sort of in the same position, then you put your point of dilation inside the figure. All right, so how do we do this in ALEKS? Well, I'm glad you asked. Oh, it timed out. I gotta log back in. Hmm. 8.1. Oh, that's not what I wanted to do. So 8.1 has 6 different problems. First up, dilating a segment given the coordinates of its endpoints. So in this problem, it says that the center of dilation is at the origin, so right there, and the scale factor is 3. So down here, I can change the scale factor to 3. And this point, which is 2, 5, so the original left endpoint is 2, 5. And if I make it 3 times bigger, 2, 5 is going to turn into 6, 15. So 2, 5 got 3 times bigger, and now it's 6, 15. The right side point is 6, 2, so I put a 6, 2 times by 3, 18, 6. Does that make sense? Now it might ask you to do a scale factor of 1/2. So you need to drag this down to 1/2 and then do your endpoints. Or it could be 3/4 or 1/4 or 1.5, whatever the instructions tell you to do. Problem number 2, are these figures, can I use a dilation to change one figure into the other? If this is a dilation about the origin, can I take the solid figure and dilate it and end up with the dashed figure? Well, I would need to change my dilation ratio. Can it be done? No. They're the same size. So that can't happen. Over here, can I dilate this so that it matches up with that one? Well, let's just try it. Yes, that would be the dilation ratio of 4. Problem number 3. What does dilation do to the side lengths of a particular shape? The dilation center here is the origin, and we're going to do a dilation of 1/2. There we go. So the longest side was 8. If we do a dilation of 1/2, how big would the longest side be? We went from 8 down to 4. So the longest side of the final figure is 1/2 as long as the longest side of the original figure. The original figure and the final figure are similar. What does it mean to be similar? Yeah, they do have something in common. What specifically? Yeah, they have the same shape. Now, having the same shape is not a very good geometric definition, but you guys understand that. What it means is it preserves all of the angles. And it also means that the sides are proportional. So, yes, those are similar. Number 4. Okay, this is a little bit trickier. Our dilation center is the origin. We start with the solid shape, and we end with, we start with the gray shape and we end with the blue shape. Now notice, we started with point D and we ended with point D apostrophe. In mathematics, we call that D prime. Or if it has 2 marks, we would call it D double prime. And that just means D prime is what happens when you change the original shape. D double prime would be what happens when you change the D prime shape. All right, so here it's asking us, the line through D and F passes through the center of dilation or does not pass through the center of dilation. So we're going to take our ruler and we're going to line it up from, what was it asking? D and F. So we're going to line up from F to D. Oh, I probably want to go the other way. So I'm going to line up from D to F. Is that line passing through the center of dilation? If I were to extend that line out, would it pass through the origin? Yes. So this would be passes through the center of dilation. Now let's look at E and F prime. Or sorry, E and F. So we look at E and F, and we also look at E prime and F prime. Does that line pass through the center of dilation? No. So what we're learning here is any line on the original figure, when extended, that would hit the center of dilation, the other line in the dilated figure is going to be along that same line. But if it doesn't, then the lines will be parallel. So DF and D prime F prime are on the same line because that line hits the origin, the center of dilation. But EF will not hit the origin. But E prime F prime is going to be parallel to EF. So you can guarantee in every figure, every line will either create a new line that passes through the center of dilation, or it will create a new line that's parallel to the original. So this one does not pass through the center of dilation. And then you'll find the slope of DF. If you know the slope of DF, you know the slope of D prime F prime. Those two are going to be the same. Same with that. So lines DF and D prime F prime are, so look at D and F. Are they the same line, they're perpendicular lines, or they're parallel and distinct lines? DF and D prime F prime lie on the same line. Okay, what about EF and E prime F prime? They are parallel and distinct. So, what is the rule we just learned? A dilation takes a line not passing through the center of dilation to a parallel and distinct line. A dilation takes a line passing through the center of dilation to the same line. All right, for this one, the center of dilation is at the origin. The factor is 3/2, which is 1.5. So we start with the gray triangle, and we end with the blue triangle. So D moved from 2, 8 to this point, which is 3, 12. Now, could I figure out those answers without the picture? How would I take 2, 8 and turn it into 3, 12? times it by 1.5. So my scale factor is 3 over 2, which is 1.5. So I can just times each of those by 1.5. Okay. So, and then you have to figure out which of these rules is going to turn triangle DEF to triangle D prime E prime F prime. Which one do you think it is? It's this one, right? Oh no, not that one. It's got to be 3 over 2 and oh, this one. This is the one we want. The x's and y's are in the right place, and both of them are multiplied by 1.5. Okay, lastly, here is a figure. Here is your scale factor, 5/3. So you would need to come over here and draw the new figure so that it was a scale factor of 5/3. That's probably in the wrong place, but all right, get to work.